up, let me introduce Pravesh in the interest of time. So our next speaker is Pravesh Kothari, who is a professor at Carnegie Mellon University. So Pravesh did his PhD from UT Austin and then spent a few years at Princeton before moving to Carnegie Mellon. Pravesh has a broad range of interests in theoretical computer science that includes understanding the theoretical foundations of machine learning. And his work has been awarded with several prestigious awards, including the Sloan Fellowship and the NSF Career Award. So again, we are very happy to have Pravesh here, and whenever this is set up, over to you, Pravesh.
Okay, perfect. Yeah, thanks, Debmalu, for the introduction. Thank you for inviting me. Thank you to the organizers for arranging this fantastic venue. So I want to tell you about, not sure if I can, okay, let's see, we'll make do with that. Okay, so I want to talk about this very recent work on new algorithms for a semi-random variant of the planted clique problem. You don't have to know any of that. I'll tell you a little bit about it today. And this is based on joint work with Raresh Buhai and David Steurer, both from ETH Zurich. Okay, good. So let me, start by telling you this basic context of this line of work. So I'm going to be interested in the problem of finding large cliques in graphs. Okay. Now, this is a very basic combinatorial optimization problem with really decades of history behind it. So I'm not going to tell you all of that. Let me just summarize, bottom line it for you, what we know about this clique problem. By the way, just to make sure we are all on the same page, a clique in a graph is just a subset of vertices with all possible edges between them. And it's a basic NP-hard problem to find such a set in a graph, and we are going to be interested in approximating it, okay? Good. So what do we know about this? So you don't have to read this translucent thingies on the slide. Suffice it to say that the bottom line is that this problem is very, very hard. And in particular, even when the graph is promised to contain a clique of size nearly linear in the number of its vertices, the best known algorithms fail to recover even a small polynomial size in the clique in the graph. And somehow this seems inevitable, because of the known hardness results. Okay, that's basically the summary of it. And if you come from an algorithm design perspective, this feels a little bit, disappointing, because it just says that the worst case model of input instances is not going to be enough for you to somehow, invent good algorithms, because there's not much space for algorithmic innovation if you work in this model. So what do? Well, a natural strategy is to work with certain non-worst case models. And one predominant strategy in this direction is the so-called average case models, okay, where you somehow consider instances of the problem which are chosen according to some probability distribution, and now you somehow try to solve instances drawn from this distribution instead of worst case instances. And the hope is that somehow this will inspire new algorithmic ideas, etc. Okay? So the most well-studied analog of the clique problem in this average case world is the so-called planted clique problem. And the input in this planted clique problem is generated as follows. You select a random graph. So this time the graph is not worst case. You select one from the GN 1/2 distribution where every edge is included with probability half independently of others. Then you introduce a k-clique into this graph. So you select arbitrary set of k vertices and complete the clique on them. Okay? And then you ask the algorithm to find this k-clique. Okay? So again, there is 30 years of work on this problem. I'm not going to tell you all of it. Again, I'm going to just highlight it and bottom line it for you. So one thing you can prove is that if you just select the random graph GN 1/2, then with very high probability, there is no clique of size larger than 2 log n in it. So the max clique in GN 1/2 is no larger than 2 times log n, which means that if you planted a clique which is much larger than this size, then such a clique with high probability will be in fact the unique max clique in the graph. Okay, so in that case, finding this planted k-clique is equivalent to finding the maximum clique in the graph, and that's the problem people think about here. Now, the analog of brute force algorithm here runs in quasi-polynomial time. So in quasi-polynomial time, you can basically brute force out some log n size subsets of vertices, check if they're a clique, and this allows you to recover, cliques of basically any size larger than 2 times log n. So the main question is, what can you do in polynomial time? Okay, so you don't have quasi-polynomial time, you have only polynomial time. And the best result that we know, algorithmically speaking, is this paper of Alon, Krivilevich, and Sudakov, who use a clever method based on eigenvectors and eigenvalues of the adjacency matrix of the graph. And they show that this method can recover the added clique if it is larger than root of n. Okay? So there's a huge gap between where we could ask for an algorithm, namely 2 times log n, and where this algorithm succeeds, which is root n. But it turns out this is basically the best we've got as far as we know. Okay? If you give me a little bit more running time, like a larger polynomial runtime, you can make the constant in front of this root n arbitrarily small, but that's as far as what we know goes. Okay? And what people have done is like try to explore whether this could be inherent, and there is like a long line of work on understanding evidence of hardness for recovering cliques of size little o of root n. So things which are like significantly asymptotically tinier than root n. And the bottom line again is that restricted lower bound suggests that maybe this will not be possible in polynomial time. Okay? So what do we know? Well, maybe a little bit more room for algorithms, maybe new ideas like spectral methods, SDPs, that you can invent by looking at this average case model. Okay? But there is always a very nagging question when you keep thinking about average case models, which is, which one is the right model? Right? Like if you came from the perspective of trying to use a model of instances to inspire new algorithms, this was just a natural model, but there are many average case models I can define. There are many probability distributions on instances of graphs or clique or whatever I can define. Which one should I work with? This is especially problematic because it turns out that our algorithms often strongly rely on the modeling assumptions of the specific random model that we are using. And in particular, break down, even if the graph that you select departs only a little bit from this random model that you've chosen. Okay? To explain this perturbation business, let me give an example. Okay? So if you look at this planted clique problem, one very simple algorithm for it is to just look at the vertices of the largest possible degree and hope for the best, as in like hope that these are the vertices in the planted clique. Now you can show that this algorithm works very well as long as k, the size of the added clique, is larger than some constant times square root of n log n. So it's almost at this root n point, maybe a root log n off, but pretty good. It turns out that this algorithm, on the other hand, is very, very brittle in the sense that if you just modify the graph in order n edges, so you're like modifying a vanishing fraction of the graph, it can completely break down because you can decrease the degrees of the vertices so that somehow the highest degree vertices do not give you any information. Okay? And this is not special to just like the degree algorithm, it's also true for the algorithm based on spectral methods of Alon, Krivilevich, and Sudakov, that you can basically like modify about order n edges of the graph, so 1 over small n fraction of the graph, and completely make these algorithms break down. Okay? So one interpretation is that somehow these methods that we have invented for solving the planted clique problem are brittle in the sense that they seem to be overfitting to these assumptions of the random model that you've made. Okay? And if that's happening, it's hard to argue that we are discovering interesting heuristics for the clique problem because we arguably are exploiting properties which are very brittle, which are very easily modifiable. Okay? So this whole discussion motivates the issue of finding robust algorithms. Algorithms that somehow do not overfit, in some intuitive sense, to the specific random model that we're working with. Okay? And that's basically the context or the major topic of research that this line of work comes from. Okay? So, this line of work has a lot of, in some sense, resurgence in some sense in several different areas of theoretical computer science in the past few years. And they're like, major problems in algorithmic, like robust statistics and smooth analysis, etc., have tried to grapple with this issue of how can we design algorithms for average case settings which are somehow robust, like do not exploit modeling assumptions, too strictly. Okay? So today I'm going to tell you about this semirandom models, which is like one approach in this, line of work, and specifically in the context of the planted clique problem. Okay? Good. So let me tell you a little bit about semirandom models in general and then proceed to tell you the model for the planted clique I'm going to think about today. So semirandom models in general, I'm sorry for the slides by the way, there is some, you go from PowerPoint to PowerPoint and things change. So semirandom models were introduced in this very cool paper of Blum and Spencer and really generalized to a whole host of problems in this paper of Feige and Killian. All of this is happening in the late 90s. And one way to think about them is that they combine certain natural average case model with a adversarial or worst case choice. Okay? So somehow in these models, an input is selected in 2 steps. The first step is like an average case or an easy choice, a random choice, okay? But then there is a constrained adversary who comes up and tries to modify the selected input instance, in order to make the life of the algorithm harder, okay? And the goal would be to somehow design an algorithm that is somehow tolerant of these adversarial, changes to the input. So such models are like very well studied for, a number of interesting and important optimization problems. And this line of work forms an important thrust in this whole area, which is called beyond worst case analysis of algorithms, that tries to escape worst case hardness by making somehow, certain additional assumptions on the inputs, okay? So, good. So, all right, so with that like prologue, I can tell you the specific model I'm going to be interested in today. This model was introduced by Feige and Killian in this paper that I was talking about earlier in 1998. And it can be thought of as a semi-random version of the planet clique problem. So the random choice in this, the first random choice in any semi-random model is like a vanilla random model. In this case, it will be the basic planet clique model, okay? So you just basically take a random graph, G n 1/2, and introduce a k-clique into it, okay? But now an adversary is going to come in and modify the graph. And let me describe this adversary in 2 steps. I'm going to call the first step the adaptive deletion step, okay? The adversary comes in and deletes an arbitrary subset of edges so long as they don't touch the edges inside of the planted clique. So the clique on S star that I've added will remain no matter what happens, but I am allowed to delete any subset of edges outside of it, okay? And in the third step, there is an adaptive addition where the adversary comes in and can add an arbitrary subset of edges as long as the edges don't touch any vertex in S star. Okay? Does this thing work? Good. Very good. So just to be, absolutely clear, let me describe this whole model, in a different way, just so that, you have some intuition building up. Here's an equivalent way to choose this model. You select a k-clique on S star. You choose the edges that go from S star into the rest of the graph randomly. Okay, that's the only random choice. Now, an adversary can come and delete an arbitrary subset of edges in the cut of S star and introduce a completely arbitrary worst case graph on the rest of the vertices. So on V minus S star, the blue part, you have no control. It could be an arbitrary worst case graph. Okay, this is the model. Okay, this is the model. Okay, this is the model. Okay, this. Was that me? Okay. As long as, yeah.
So I could add another clique in V minus S.
Exactly. So let's get to this point. Let's explore this model a little bit. In the first step, if I add a clique of size k, which is much larger than 2 times log n, then in the first step, the graph's maximum clique would indeed be the planted clique. But now, what Anupam is observing is that if I do these steps 2 and 3, the status of the max clique itself is going to be a little bit, different. And so we're going to explore these kind of issues in the next 5 minutes, okay? Let's start with the easy thing. If I omit steps 2 and 3, then I get the average case model back. So it's good. It's a generalization of the average case model, okay? If you omit step 3, which is like you're not allowed to add edges, you're only allowed to delete edges from the random graph, then you get a model which is also very well studied and is called a model with planet clique with helpful monotone adversary, okay? And this particular monotone adversary setting is also very well studied in the context of other problems. The reason it's called helpful is because deleting edges from the random graph outside of S star cannot possibly, for example, change the status of S star as the max clique in the graph, because you cannot introduce new cliques. In fact, this is true in a strong sense. So the following sentence may or may not make sense. Feel free to reject it. If you take, for example, if you try to, introduce, if you started with a graph on V minus S star, which is not a hard instance, let's say, for example, is not an integrality gap instance for an SDP or whatever, then deleting edges cannot make it one. So in that sense, you cannot introduce cliques, you cannot introduce things that even pretend to be cliques. So in that sense, this adversary can only try to help you. Despite the fact that the adversary is potentially only helping you here, it turns out that these heuristics that I was talking about, this algorithms that people use in this context, degree-based algorithms or eigenvalues, they break down completely. And so, it was, in some sense, the first question that was studied in this direction, and it was resolved already like 20 years ago in this work of Feige and Krautgammer. And they basically showed that if you depart from this basic heuristics, don't use degrees, don't use eigenvalues, but rely on a certain SDP relaxation. It's the most natural relaxation that you can write in this context, but I'm not going to tell you what it is. Then it has a natural rounding algorithm that works exactly at the same threshold that, the algorithms for average case parent clique work. So that's kind of great. Like, you lose nothing. You just have to, upgrade your algorithm to a more robust version. Okay? Good. So now if we come back to this full model, this model turns out to be like now much more challenging. And one aspect of why that might be true is that because the adversary can both add and delete edges in the graph, as Anupam observed, the added clique need not be the max clique at all. Because I can introduce like, a whole new clique on V minus S star. The graph on V minus S star could be like an output of a reduction from 3 sat into clique. The V minus S star could have like many, many larger cliques. So, the added clique need not be the largest clique in the graph. The added clique, for example, need not be easy to find via SDP relaxations because the SDP relaxation, etc., could focus entirely on V minus S star. So in some sense, this problem is, this setting becomes much more challenging. Actually, even before it becomes much more challenging, we should ask, what should be the goal? What should be the goal even here, right? Like, if I ask you to find max clique, of course we are doomed here because V minus S star could just be like the hardest possible instance of the clique problem, in which case we should really not be able to do anything better than what is known for the worst case. So, what's even the goal? So I'm going to focus on 3 possible goals, okay? And as I'll soon, I'm just going to assert that the third goal is somehow the most general one, and that's the one I'm going to focus on. It implies all the others. But first start with the first one. The simplest goal you can think about in this setting is to find a k-clique in the graph. Okay, so I'm not going to focus on the max clique. The max clique could be larger, but my goal is to find a k-clique. The hope is that somehow S star is somehow still easy to find. So if I could find that, it would be a k-clique. Now, S star is not uniquely identifiable in general because the adversary could simulate this random model inside V minus star, S star like many times over. So really, I can't ask the algorithm to find S star uniquely, but I'm going to be okay if it finds a k-clique. More generally, if you give me like some additional information about S star, like a uniformly random vertex inside it, then maybe I can even find S star. So that's the second kind of guarantee. And finally, the guarantee I'm going to focus on today is to actually find a list of k-cliques in the graph with the property that the list is no larger than n over k in size, and the list is guaranteed to contain S star. So this is like somehow resolving this issue of the fact that S star may not be uniquely identifiable, but as long as I can produce a small list that always somehow contains S star, I'm going to be happy. And you should think of this n over k as the number that arises if you try to cover the graph with disjoint k-cliques, which is roughly the intuition. That if I somehow like try to get many almost disjoint k-cliques, somehow S star would be one of it. Okay? So I'm not going to like describe too much detail. It's easy, but I'm not going to spend time on it. That this third guarantee is the most general one here. Like if you get it, you get all the others. Okay? So that's the one I'm focused on. Yes, Anu? Yeah, so they won't be disjoint, but they would be almost disjoint. So therefore, I get 1 and 2. But yeah. Good. So let me tell you what is known about this problem. So I already told you that if you try to round just the natural SDP relaxation one can write for the clique problem, you won't succeed just because V minus S star could be a gap instance. So what people do here in the previous works is like they write some SDP relaxations with some additional constraints or like some modifications of this low-watt SDP, invent some rounding algorithms and analyze them. Okay? So the first improvement over this original paper of Feige and Killian happened with this Cheriker, Steinhardt, and Valiant's work. And they showed that if the added clique S star is of size n to the 2/3 times some log factor, then in fact polynomial time algorithms can find them. Okay? So we've like departed from this square root of n threshold and made it n to the 2/3, but at least we now have an algorithm. Okay? But somehow, this problem becomes significantly different and interesting. So, in a paper right after this work of CSV, Steinhardt proved I couldn't possibly hear.
Which goal is it addressing now?
Which one? The lower bound?
No, the previous.
So all upper bounds basically achieve all 3 goals. So, so you should think of the third goal, which is like the best goal you can think about in terms of algorithms here. So the algorithms always talk about like the third goal. Good. But the lower bound, like, your question is like even more interesting in the context of lower bounds. Only the third goal makes sense, when you want to talk about whether the list is uniquely identifiable, etc. Right, like the find a k clique, etc. is like a worst case problem, but you can ask about whether a list containing S star is identifiable. And it turns out that for that version, even information theoretically, even if you wanted to don't care about running time, you need the added clique size to be root n or larger. So, this is like much larger than the 2 log n threshold which holds for, the vanilla random, average case model. So somehow it seems like the nature of the problem has changed a little bit. Like it's become a little bit different from the average case model because even information theoretic threshold has changed to root n instead of 2 times log n, okay? All right, and the state of the art is this work of McKenzie, Mehta, and Trevisan from about 4 years ago. And they show that there is a polynomial time algorithm that works so long as k is larger than n to the 2/3. So they basically shave off this log factor. And there's also, this slight, slightly weaker model that CSV worked in where like step 2 was not allowed, and MMT's algorithm actually handles, this strongest possible model and also removes the log factor. So to summarize, basically even information theoretically the problem seems to become, hard below root n. And algorithms seem to break down at n to the 2/3, and there is a reason for it. Hopefully I'll get to a theorem which, gets here. But it seems like there is a barrier that seems to exist at n to the 2/3, which seems to suggest that something interesting is going on over and above the average case planet clique model in this question. Okay? So, given all this status of the work, Steinhardt and then Feige posed this as an outstanding open question. It's like, can you find algorithms that work for k which is below n to the 2/3? Or somehow is there a reason that this problem has become harder? Okay, and so Feige, for example, posed this question in his survey that appears in this Rough Gardens edited volume. And the main result of this particular talk is that morally speaking, you can approach the same threshold of root n as is true for average case planet clique. So somehow you can actually beat this n to the 2/3, and you can get a recovery algorithm that works arbitrarily close to the n to the 1/2 threshold. Okay. So more precisely speaking, for any epsilon, there is an n to the 1 over epsilon time algorithm that works whenever k is larger than n to the 1/2 plus epsilon. So you don't get to root n in polynomial time, but you approach it. Okay? Does that make sense, the result? Okay. So I'm going to tell you a little bit more, like some comments about this result, like some aspects that I really like. And then I'll tell you a little bit about how it's proven. Okay? So, for those of you in the know, this is not supposed to be like a understandable comment if like you already don't know what sum of squares hierarchy of semi-definite programs is. But if you heard of that, then this algorithm is based on this, sum of squares hierarchy of tightenings of SDP relaxation, starting from this basic low wash SDP. So it's like in some sense, the point I'm trying to make is that it turns out that all these ad hoc SDP relaxations that the previous works were considering are not really necessary. You can really start with a vanilla low wash SDP and strengthen it, via this systematic hierarchy, and it turns out that's enough to basically, get closer to n to the 1/2. There is something quite surprising about the fact that this order 1 over epsilon round strengthening of SDP works. So it turns out that this is in fact the very first example of a combinatorial optimization problem where higher constant degree sum of squares, which is like polynomial time algorithms from this hierarchy, seem to give a substantial improvement over the performance of the basic SDP relaxation. Okay? So let me try to make this point a little bit more clearly. It turns out, it's somehow the nature of some of these combinatorial optimization problems that either like this some basic SDP, some vanilla SDP you can write for most problems, either it works to give like a great guarantee, or you require super polynomial time to beat it. In this case, somehow it turns out that spending more running time, just like larger polynomial running time, seems to actually substantially help you beat the guarantees of the basic SDP. So this is like a first in this kind of world, so that's kind of interesting. In fact, if you go to the fully random, the average case model, there we can prove, lower bounds suggesting that this cannot possibly happen. So we actually can prove that, you cannot possibly beat the guarantees of basic SDP by going to higher degree relaxations. But, for this semi-random version, it turns out that actually strictly provably helps. Okay? So, this algorithm actually relies on lots of recent progress that is happening in algorithmic robust statistics, especially in this field of list decodable learning. So, this algorithm itself actually builds on some of this list decodable learning algorithms that, we were able to obtain in the last few years. So it's kind of nice application of how like learning related results seem to apply to combinatorial optimization. Finally, there is a version of this result that holds for, models which start from G and P for P not equal to 1/2. I'll not tell you about it today. And, there are lower bounds in the restricted models that suggest that whatever we are getting is more or less tight. It's some weak evidence, it can be beaten, but it probably suggests that you need some new ideas. Good, so I'm going to move on and tell you a little bit about how it all works, but I can pause and see if there are any questions so far. Okay, good. So recall what our goal is going to be, okay? I'm going to be given a graph chosen from this semirandom planted clique model, like this 5K Killian model. And my goal would be to somehow, in polynomial time, construct a n over k size list of k cliques in the graph, such that one of them is guaranteed to be this planted clique S star. Okay, that's my goal. Okay, good. So let me tell you, roughly how I'm going to try to like tell you about the ideas in this work. First, we will focus on the task of designing a algorithm. Okay, we won't care about the running time of this algorithm at all. You'll see that even coming up with an inefficient algorithm that provably achieves this goal of getting a list of small size that contains S star is actually somewhat non-trivial. So we'll focus on that. Okay, and I'll do it in a way that reveals this key conceptual connection to a certain refutation problem. I'll tell you all about that very soon. Then we'll focus on this refutation problem because there is a black box reduction to it. So we'll focus on like this problem and see why previous approaches really have a good reason to get stuck at n to the 2/3. So this somehow demystifies what's going on in this previous works. And then I'll give you a new approach which I call a geometric approach that actually allows approaching this root n thing. Okay, that's roughly the plan for the rest of the talk. Good. So let's see how to design an algorithm when you don't have to worry about running time. This is literally the opposite of Jelani's talk. It's like, you want to, like Jelani was really interested in designing algorithms that work very, very fast. I'm going to talk about designing algorithms that, you don't even have to worry about running times, okay? So yeah, so that's the question, right? Like, how do you recover a list if I don't like, tell you any running time constraints? How might you do it? So one natural idea is to simply enumerate all possible k cliques, right? Like, if I don't have a running time constraint, that seems like a reasonable thing to do. I have nothing that bars me from finding k cliques. But there's an issue. What's the issue? Because V minus S star has a completely worst case graph on it. In particular, there could be exponentially many k cliques in V minus S star. So the list size could be as large as n to the k. So this trivial approach, which one might think is a natural one to go to, actually does fail, right? So what should we do? Well, one natural idea is to not enumerate all k cliques, but actually to enumerate only those k cliques that satisfy some additional property. Okay? The hope would be that S star, the planted clique, satisfies this property, so that if I were to enumerate cliques satisfying this property, S star would be contained inside it. On the other hand, if I take any graph and try to count the number of k cliques that can satisfy this property, hopefully this cannot be too many more, right? Hopefully these are only n over k. So if these 2 points held true about the property I chose, then I would get the result I want. Okay? So let me tell you this property. It's actually very simple and natural. I'm going to call a k clique in the graph G L good, okay, if every other k clique in the graph intersects S in at most L vertices. In other words, a k clique is good if every other k clique is almost disjoint from it, intersects it in at most L places. Okay? It's actually very easy to prove, this is like some simple Chernoff and union bound argument, that S star, the planted clique, is actually L good if you select L to be about constant times log n. Okay? Now this is very easy to prove, and I could give it an exercise in like a randomized algorithms class or something, but I will bore you with the proof because I'm going to develop something that is essential for me in telling you how to design an efficient algorithm later. Okay? So suppose we want to prove that S star is L good. So suppose not, okay? What does it mean? It must mean that there is some other k clique T in the graph that intersects S star in more than L vertices. Yeah? So here is how I'm going to think about this, set of vertices. I'm going to consider the following bipartite graph. I'll start from the graph G I was given, and I'm going to draw the bipartite graph where the left side is the planted clique, and the right side is the rest of the vertices. So I'm going to forget the internal edges to S star and V minus S star. Okay? Good. Now, when I look at this bipartite graph and overlay this purported K-clique T that intersects S in L or more positions, then here is how it must look, right? Some part of T lives in the left part, some part of T lives in the right part. In particular, T intersect S star lives in left, T minus S star lives on the right. And because T is a K-clique, there should be all possible edges from T intersect S star into T minus S star. In other words, T intersect S star versus T minus S star must be a bipartite clique in this bipartite graph. Okay? So now, I want to, if I have to rule out the existence of such a T clique, what do I have to do? I have to prove, if I could prove that in this particular bipartite graph, there is no bipartite clique where the left side is of size L, right side is of size K minus L, then I'm done. Good? So, here is how I can argue that. First, I observe that if there was no deletion step, remember that, in the cut edges, I select them randomly, then delete. I don't add. So if there were no deletions, then it's a random graph, and you can argue that there is no L versus K minus L clique by just like, union bound. Okay? Then, you observe that deletions can't possibly introduce cliques. So you're done. Okay? So this was like the long form of the simple proof. Very good. So that satisfies the first goal, that S star is L good. Now I have to argue why, if I were to enumerate only L good cliques, the list would be small. Okay? The proof is actually very, very simple. The idea is very simple. If you look at a list of K cliques, which are all good, then no pair can intersect in more than L positions, right? Because they were all L good to begin with. So I have a collection of sets which are almost disjoint. And if you correctly set up the parameters, then there basically cannot be too many such sets. Okay? And so if you do this calculation, it's actually very, very simple. You just try to argue, what happens by inclusion, exclusion to total number of elements covered by this almost disjoint sets. You can prove that the number of such sets cannot be more than 2n over k if you start from k, which is some constant times square root of n times L. Okay? This is very, very easy. If it is very, very easy, why am I calling it the fundamental lemma? Well, that's mostly an inside joke. So over the summer, we were trying to come up with various approaches that prove bounds on L. And each time we got a new bound on L, we wanted to plug it into a formula to see what k could be handled. And we were doing this over and over again. So at some point we said, we started joking about it, saying it's the fundamental lemma that we're applying again and again. So it's a very trivial idea, but it's fundamental because of the number of times we had to apply it. Okay, good. So once you have this and you plug in the fact that S star is L good for L which is log n, you immediately get that there is an inefficient algorithm that works as long as k is at least square root of n log n. Okay? And in fact, if we didn't care about the running time here, but you can actually make it run even quasi-polynomial time if you do it a little bit cleverly. Okay? Very good. So now I want to go from here and tell you a little bit about how this approach inspires an efficient polynomial time algorithm. Okay? So the key thing would be to go back to this step that we argued using Chernoff and union bound. We looked at this bipartite graph of S star versus V minus S star, and we proved that, by union bound, that there is no L versus K minus L bipartite clique in it. Okay? It turns out that for finding an algorithm, finding an efficient algorithm, we need a way to verify this property about bipartite graphs in polynomial time. Okay, so given a bipartite graph, we want to be able to verify that there is no L versus K minus L bipartite clique in it. One easy way to do it is just go over all possible L subsets and check that there is no clique, but this would take exponential time in L. Our goal is to somehow verify the absence of such L by K minus L bicliques in polynomial time. Okay, so here is a more precise version of the problem. I'm given a k by n bipartite graph. Remember that the parameters are basically coming from S star versus V minus S star. My goal is to output a number L such that L serves as an upper bound on the left side of the best bipartite clique in this bipartite graph. Okay? So if I output L, it should definitely be true that there is no L by K minus L, or K minus L is about K in our setting, so L by K by clique in this graph. Okay? So notice that the first three parts don't posit that H is a random graph or anything. So the first three parts should hold for arbitrary bipartite graphs H. The last guarantee, which is the usefulness, says that if in addition H was a random graph, H was chosen from a K versus N bipartite graph where each edge was present with probability half, then the algorithm must output a small value. So L should be ideally log N, but we make do with small values. Okay? Notice that if such an algorithm holds, if such an algorithm exists to solve a certification problem, and it outputs L, which is like log N, then we basically, such an algorithm serves as a certificate or a verification that the input bipartite graph did not have a L by K by clique. So if we could actually have an algorithm that does it for L, which is about log N, we would succeed. Does the question make sense, like the certification problem? Okay, very good. So just to remind you, here both the cliques we are looking at and the graph we are given as input are random and unbalanced bipartite graphs. Okay, good. So as we saw before, for L, which is log N, we can verify this in quasi-polynomial time just by brute force search. And in some sense, it's a problem that in principle could have been interest to us even without this application. Like people study refutation problems quite a bit, and the balanced version of this problem, for example, is already well studied, but for some reason the unbalanced version wasn't, and it arises naturally in this context. Okay, good. So now you can, maybe I'll just rush through this slide because it's not that important. This slide just says that if you can solve the certification problem, then in fact you can get an algorithm for semirandom planet clique. And this, this method that converts a solution to the certification problem to an algorithm is completely black box. It doesn't need, information about how you solve the certification problem as long as you can solve it. Okay? And this relies on sum of squares, etc., which, I'll skip. Okay, so, good. So, now let me tell you about, how to solve the certification problem a little bit. Okay? So, first, let me, tell you how people think about the certification problem when, your input is not a random bipartite graph, but in fact just a standard random graph, a Gn 1/2 graph. Okay? So, in a random graph G from Gn 1/2, let's say you want to convince someone that there is no large clique in it. How would you do it? So, if you had quasi-polynomial time, you could just go and check that there is no 3 log n size clique in it just by brute force search. But if you only had polynomial time, then here is the best known method that we know. Okay? The best known method basically observes that in any graph G, you can bound the maximum clique size in this graph G in terms of the largest singular value of its adjacency matrix. Okay, so this, this is some basic connection between the largest clique in a graph to the largest singular value of the adjacency matrix. Okay, and this has a very simple proof, but I'll skip it. Once you have this proof, you observe that if you use this bound for a random graph, then because of A being the adjacency matrix of a random graph, the largest singular value of A turns out to be about square root of n. And that is basically the reason, this bound certifies something about root n. And it's the same, it's basically the reason why, we can find root n size planet cliques, but nothing smaller. Okay? So now you could ask, what happens if we do the analog of this argument for our setting, for the unbalanced bipartite setting? Okay? I'm not going to do the proof for you, but it turns out that if you do the math, you actually get a result that works only when k is at least n to the 2/3. Okay? And this is like a very simple argument. But you can if you just run it again, it turns out that the threshold here turns out to be n to the 2/3 and not n to the 1/2. And in fact, you can prove that it's not like we just got unlucky with the choice of the matrix or something. Even if you try to use a different matrix, there is a lower bound that says that basically you can't possibly beat the guarantees of this argument. Okay? So it seems like this is somehow the heart of the reason why this previous works were getting stuck at n to the 2/3. Okay? Good. So let me also skip this. So in the last, let's see, 5 minutes or so of the talk, I want to tell you actually the kind of certification, the kind of algorithm that actually solves the certification problem and gives us our result that approaches root n. Okay? The idea is actually very, very simple once I tell you this connection, okay? So I'm going to call this a geometric certificate, okay? And here is what, the key lemma says. I'm going to show that if there is a large bipartite clique in a bipartite graph, okay? Right now I'm talking about a random graph, but we'll soon see that, we will replace this by a very simple to verify deterministic condition. But right now let's work at the level of a random bipartite graph that we were given. I'll prove to you that if there is a L by K biclique in a random bipartite graph, then I can produce a set of vectors in n dimensions, okay? So you should think of the dimension of the vectors as the size of the right side of this bipartite graph, with the property that every pair of these vectors is negatively correlated. So the inner product between every pair of vectors is strictly less than 0, okay? Why does that help? It turns out that there is a very basic geometric fact that says that if I want to pack the largest possible number of vectors such that every pair has inner product which is strictly less than 0 in R to the n, then you cannot have more than n plus 2 vectors. In fact, you cannot have more than n, so you can have n plus 1 vectors but not n plus 2. The n plus 1 vectors, by the way, are just the corners of the standard simplex. So they basically are negatively correlated, and there is nothing better you can do. Okay? So now, if you plug in this lemma that says that if there is a L by K biclique, then for any t I can produce basically about L to the t pairwise negatively correlated vectors in R to the n, along with this fact, then it tells me that L choose t should be at most n plus 1, which means that L should be at most about n to the 1 over t, and if I choose t to be about 1 over epsilon, then it says that L should be at most n to the epsilon. So in particular, if I plug in this bound on L with the fundamental lemma that says that I need k which is about square root of NL, this gives me, a algorithm for semirandom planet clique with all the machine, when you run all the machine, that works whenever k is at least n to the 0.5 plus epsilon. Okay? So this connection is very, very simple, so I'm going to give you the proof of it, okay? And that will be the last thing I'll do. Good. So I'm not going to explain this to you, but it turns out that this particular kind of certificate can in fact be checked efficiently. This is where SDPs or sum of squares, etc. comes in. But because the geometric fact is enjoyable on its own, I'll only prove that to you and skip all these details. Okay? All right. So I want to somehow show you that if there is a bipartite graph like this, right now we are still considering random bipartite graphs, and there is a L by K biclique in it, then I can somehow manufacture from the existence of such biclique L choose T different pairwise negatively correlated vectors. Okay, that's my goal. Here's how I'm going to do it. I'm going to define the following kind of vectors. I'm going to call it n sub z, where z is a subset of vertices on the left hand side. So for all possible subsets of vertices z on the left, I'm going to define a vector nz. The dimension of this vector is n, so it's equal to the right hand side size, and the coordinate at j is basically the product of all possible edges, indicators of all possible edges from vertices in z into j. Okay, so there are size of z such edges. I take the plus minus 1 indicator for every such edge and multiply them out. So in other words, this nzj vector computes the parity of the number of edges from the set z into j. Okay? Good. Now, here is what you can prove. In a random graph, if you take z and z prime, which are distinct subsets, and compute the inner product, then because of some simple union bound argument, the inner product of these vectors is no larger than some square root of n log n. Okay, so all these vectors are almost uncorrelated. But this is not, you can have exponentially uncorrelated vectors, such uncorrelated vectors in n dimensions, so it's not somehow going to give us our result. Okay? What I'm going to do, I said, that this is all about a random graph, but this is all the property I need. So in the end, my tester would simply check that if I form this n sub z vectors, then the inner product is small. Okay, that's going to be my verification at the end. Anyway, so if I start from this, fact that for distinct z and z prime, the inner product of nz and nz prime is small, here is how I can construct negatively correlated vectors. I observed that if I look at nz and nz prime, and look at the coordinates j that lie in the right side of the clique, then and if I start from a z which is a subset of the left-hand side of the clique, then because j is in the right part of the clique, all possible edges from z into j should be present. Which means that in the k vertices that correspond to the right side of the clique, both nz and nz prime have +1 written in them. Which means that the contribution to the inner product of this green part to nz dot nz prime is plus k. Okay? That's what that sentence says. Which means that if I now just take the vectors obtained by just stripping off these k coordinates, remove the k coordinates that come from this green part, the part that is in the right clique, then the inner product of nz stripped off of this k coordinates with nz prime stripped off of the same k coordinates must be at most root of n log n minus k, because earlier this part was contributing plus k. And now if k is bigger than root n log n, this is strictly less than 0. That's it. Okay? And so, but just with this connection, it turns out that you get a very simple certificate. You simply verify that all possible inner products like this are small, and you get the solution to the certification problem. Sorry. I thought it was a raised hand. Okay, so let me finish with just like a summary and takeaways. So yeah, so I showed you how to approach the same threshold for the average case planet clique problem even in the semi-random setting. What I like about this kind of models and the algorithms that come out is that they kind of narrow the setting where the worst case clique problem remains hard. So look at the worst case clique problem, and you could ask what makes the worst case clique hard to find. So of course the problem is hard in the worst case, but what this result is saying is that, well, only the randomness in the cut edges of this purported clique that you're trying to find governs efficient findability. So it somehow says that the problem might be hard in the worst case, but as long as somehow the edges going outside of a large clique are benign, like they are not somehow ganging up against you, the problem is actually way easier. Okay, so it's somehow like some kind of an insight about what's happening to just even the worst case problem. As I said, the conceptual key is this connection to refuting unbalanced bicliques. Also, I guess both of these points I guess I made earlier. So let me end with this, last picture slide, which is like, a spiel for the kind of work I'm doing, in the last 2-3 years. This is the kind of slide I show new students at CMU these days, which is like, how can you somehow start from this average case algorithms, average case analysis, and build algorithms which are significantly more robust, significantly more general, don't somehow overfit to the random model. And such problems are actually present in many different areas, not just combinatorial optimization. I think there's a lot of great work to be done here.
Thanks, Pravesh. Any questions for Pravesh? There is one.
Okay, so I think I caught a few words. Let me maybe say the following point that might be relevant. In this adversarial choices, the adaptivity is really important. For example, if you change the order of this model in which you first choose, like, let's say, the adversary's choices and then choose your random edges, then the model turns out to be significantly easier. So somehow, the fact that we are giving adversary the control over how to modify their edges as a response to the random choices is really important. Does that answer your question?
I think so, yeah. I guess the hope is that we're moving towards the worst case, but then if you want to do it obliviously, you're going towards the average case instead. So that's.
Yeah, this is also how I view it. I feel like we are tightening the regime where the problem could remain worst case hard. Like hopefully we can push average case as far as we can go, and then okay, maybe some small area where we can't solve the worst case problem will remain, but also maybe we not be so disappointed with it. In fact, like in the open problem session, I'll suggest like a generalization of this as a problem, which further somehow. Yeah, there is like a natural generalization of this model where you can ask this question, which tightens the regime for the worst case clique problem to remain harder even further.